In chapter 5.2, we're going to look into bisectors, and this is going to get you ready for what you're going to be doing in 5.3 and 5.4 when we're figuring out all the different centers of triangles. So the perpendicular bisector theorem, although we haven't covered this yet, it is going to be somewhat familiar to you, because you know that if you take an angle bisector that bisects the vertex angle of an isosceles triangle, then you know that it's also the perpendicular bisector of the base. Well, that's very, very similar to what we're doing here. If you have a segment, say AB, and you bisect it with a perpendicular bisector, in this case, line PM, any point that is on that line is going to be equidistant to either of the endpoints of the segment. And it's basically creating an isosceles triangle with segment AB being the base, and then sides or segments AP and PB being what would constitute or make up the sides of the isosceles triangle. Now, equidistant, just think about the two parts of that word. Equa meaning equal, and then distant, distance. So they're equally distant from, or that point is going to be equally distant from those two endpoints. So we know that the distance between P and B is the same as the distance between P and A. Now the converse of that theorem just means that we're going to go backwards. So if a point is equidistant from the endpoints of a segment, so we don't have a perpendicular bisector drawn, but we know that point P is the same distance from A as it is from B, therefore it's creating an isosceles triangle, then we know that point P has to be on the perpendicular bisector of that segment AB. So let's look into how this theorem is used. In problem number 1, we've got what is the length of segment AB. So what we see is that we've got a perpendicular bisector that is BD. AC has been bisected and BD runs at a perpendicular angle to AC. What that tells us is that the segment AB is congruent to segment BC. So we can take the values 4x and 6x minus 10 and set them equal to each other, solve for x, we get x equals 5. Then we take that 5, put it back into one of those, so 4 times 5 is 20. So we know that segment AB is 20 units long. Problem number 2 has been modified from the book just a bit. We've got the Busch Gardens general manager wants to build a new restaurant equidistant from Kumba and Montu. What are the possible locations of the restaurant? So on this map, I've marked off Kumba with a K, Montu with an M. Then you have the Lions with an L and Shikra with an S. So to decide where this restaurant could be built, what we're going to do is draw a line connecting Kumba to Montu. So this is the segment that we need to bisect. So when we draw that perpendicular bisector of that line, what we can see is that that perpendicular bisector is intersecting some of the paths in the park. So what you would do is you would highlight the paths where the perpendicular bisector crosses the paths, and you can see those are the 3 locations where you could build a restaurant that would be equidistant to both Kumba and Montu. Now the next thing you need to know is the angle bisector theorem. So if you've got an angle and there's a bisector for that angle, then any point on that bisector is going to be equidistant from the sides of the angle. Now the key here is that you need to know one specific rule. the shortest distance between a point and a line is always a perpendicular line. So you can see that we have the point S is on the angle bisector. So the shortest distance to line QR, or I'm sorry, to ray QR, is a perpendicular line, or in this case, a perpendicular segment SR. Then the shortest distance to ray QP is going to be segment SP, which is also perpendicular to segment Q, or to ray QP. So remember that anytime that you're dealing with the shortest distance between a point and a line, you're always talking about a perpendicular line or a perpendicular segment. Now, the converse of this is that if you have a point that is inside of an angle, and you know that that point is equidistant to two other points, so in this case, S is equidistant to P and S is equidistant to R, then that tells you that S must be on the angle bisector, so you can draw a line, a ray, or a segment through the angle and through the point S, and that's going to tell you that angle PQS is congruent to angle RQS. So here in problem 3, we're asked, what is the length of segment RM? And what we see is that angle MNP has been bisected by ray NR. We know that because we've got the congruency markings down in the bottom. Then we also know that segment MR is congruent to segment RP. Now, since R is on the angle bisector, and R is equidistant to M and P, we can then say that 7x is equal to 2x plus 25. Then we can work that out, and we get x equals 5. So if we want to know what the length of segment RM is, then we just plug 5 in for x. 7 times 5, 35, and there's your length for segment MR.